Yes, so yesterday was a lecture 6 where we covered the classical complexity classes. There we covered a bit of along with the NPP, all the classes. We also covered a part of the theory from automata. We also have seen the problem space, solution space, and what are feasible solution, infeasible solutions. And post that we have seen a part of the SAT problem, satisfiability problem. Also, what do we call by a deterministic Turing machine, which is an unrestricted grammar and a non-deterministic Turing machine, and how the DTM and NDTM are related to the performances or kind of a relation what they have with the P and NP class. Post that we have seen the NP hard and NP complete, at least the definition. So yesterday, where I ended is exactly that I told you that we will be discussing a bit of that how really exponentially hard or a hard problem in classical looks like. So for that, I will be choosing today the traveling salesman problem. That will be the part that I will start today first. I will show you that why exactly, even if we apply the best known algorithm, which is not an approximation algorithm, and why it is a hard problem, despite of applying the best known classical algorithm. We will see that after that, all the normal complexity classes will be covered, which is kind of a deterministic complexity classes will be covered. Post that, I will enter into what is the in-between thing, like a classical and a quantum, which lies the classical randomness theory. Based on that, there are a few complexity classes which are known as classical probabilistic complexity classes like BPP and PP. We will cover that. And we will introduce the concept of the quantum complexity classes, where primarily we will be covering these three, which is a BQP, QMA, and QCMA. And a few more complexity classes are there, which is kind of an advanced one or kind of derived version of all these three, which I will try to mention. So this is what today our agenda is, or what we are going to cover. Okay, without any further delay, let us start. So the first thing was a TSP. I have given you a problem definition kind of stuff for TSP yesterday also. The full form of TSP is traveling salesman problem, where we believe there is a kind of a salesman who will be traveling in all cities of a town, and there is a constraint that he has to visit all the vertices exactly once. He cannot skip any vertices, but if needed, he can skip some of the edges. But the target is, after visiting all the cities or all the vertices of the graph, he has to ultimately come back to the original vertex, which was the source vertex. And this problem is also in maths term, it is known as a Hamiltonian cycle. So the optimization version of TSP, as we discussed yesterday, it was kind of finding the optimal tool. What do I mean by optimal? I've told you that optimal can be described in two senses. It can be either maximal or it can be minimal. Whenever we call optimal for in context of TSP, it means the minimal tool. So here optimal basically means the minimal tool. Minimal tool. Okay. So minimal tour means there will be some cost associated, and our ultimate target will be, if it is a source vertex, covering every vertex of the graph, I have to come back to the source vertex with the minimum cost. So if this is say W1, W2, W3 and W4, and say this is W5 and this is W6, ultimately maybe say W1 plus W5, W1 plus W5 plus W3 plus W4 is my minimum one. So this is the minimum cost. Okay, cost 2. So this is what you are about to find. But the thing is that since there is no fixed one that with which vertex I can start with, which can be my starting vertex, since that is not fixed. So if we do not apply any very clever technique or any very strategic technique, then generally it is going to take a factorial amount of time. Because of course, I can start with any of these vertices as my starting vertex. Okay, but this was definitely exponentially very high, which is n to the power n. I have described that why n factorial is a big O of, or it belongs to the big O of n to the power n. What is big O notation and why we call it is like belongs to, and this is a complexity class of n to the power n where n factorial belongs to this one. So this is when we apply a brute force approach. So it's kind of, we take up all the possible combinations and we try to find that which one is our best solution, right? But in classical itself, there has been an advanced approach existing, which called the DP version, or dynamic programming version of dynamic programming approach or version of TSP. DP version of TSP. So what it does, it uses kind of a technique known as a memoization technique. So the technique is pretty simple, that we try to find the optimal substructure property. Optimal substructure property. Which is, in a very easy language, it is, if I have to find a very solution of a very large problem, and if I divide it in smaller sub-problems, then each of my smaller sub-problems, if I take it directly as a value, and directly I use its reference, it will ultimately aid to the bigger problem. So that is kind of a part or a component or a subcomponent of a bigger problem, which is a smaller problem, that also is an optimal solution. So that is the optimal substructure property in a very easy non-mathematical language. Okay. So to find the optimal solution of a bigger problem, we will be relying, or we can rely on the optimal solutions of its components or optimal solution of its subproblems. Right? So on that note, what we do is we try to decompose, or we try to express the entire search space of TSP. Okay, then if there is any repetition in terms of the sub problem, we try to take that. And instead of TSP, we can think it of as a very general problem. Let me give you a very general problem example where we know it, like say factorial of a number. So factorial of a number. Now you know that, say factorial of 5, if you want to calculate, it ultimately is what? 5 into factorial of 4. Factorial of 4 is nothing but 4 into factorial of 3. Factorial of 3 is nothing but 3 into factorial of 2. Factorial of 2, whenever it is called, it is nothing but 2 into factorial of 1. And this one ultimately, if I end here, it will be 1. So likewise, it ultimately, in the recursion, we will go back, and ultimately here it will be likewise computed. Right? So these are all the recursion calls that we have to do normally. But in case of the memoization technique or dynamic programming, what we believe is, instead of making this, and which will ultimately yield to an n factorial time complexity, okay, what if we can do it in this way? Say, whenever I'm calculating factorial of 1, I will be storing it somewhere. So, say at an instance, I want to calculate factorial of 5. So my factorial of 1, 2, then factor of 3 and 4 should be there with me. So factorial of 5, while calculating these, I can directly, it's an integer 1, I will take this up and I will directly take the value of factorial of 4. So this is a value that I will be taking, not directly, I'm again incorporating the function call, which is a factorial of 4. So factorial of 2 will incorporate 2 into factorial of 1. Factorial of 3 will incorporate 3, then factorial of 2, then again factorial of 1. So see, factorial of 1 is a repetition because it is also there for factorial of 2 as well as it is again there for factorial of 3. Similarly, if I go one step ahead, factorial of 4, in normal approach, it is ultimately incorporating factorial of 3, which again is incorporating factorial of 2, factorial of 2 again incorporating factorial of 1. But do I really need that? I don't need it. Why? Because factorial of 4 is nothing but 4 into factorial of 3. So if somehow I manage to store the value in a temporary memory space or an auxiliary space somewhere, the value of the factorial of 3, then directly I can use that value. And it will be ultimately then a 4 into 6, which is 3 factorial. And in order to get the value of factorial of 4, it will be directly 4 into 6, where 6 value I will be getting from this. So if I get this one, so in order to for factorial of 4, so it will be 4 into this 6, which I will be getting, sorry, this is 3, sorry. So this 6 I will be getting here, so it will be ultimately 24. So this is an auxiliary memory space. So definitely it increases some amount of auxiliary space, or increases a part of a space complexity, and it makes it order of n, but also it helps to reduce the time complexity, which was initially n factorial, to only n. So this is kind of a polynomial time reduction, sorry, not a polynomial, it's an exponential time reduction. From n to the power n, right now it's a big O of n only, right? So that is the power of, say, dynamic programming. Okay. Now, this was for the factorial. And why, see here, why, understand the why here. Why we are able to get the benefits of dynamic programming is because we can have access of some repeating problem. Like factorial 3 has a repeating of factorial 1. And factorial 2 has a unique problem, which is factorial of 1. But factorial 3 is a repeating one, which uses a repeating subproblem, which is factorial of 1. Why repeating? Because it is already there with fact 2. Similarly with fact 4, with fact 5. So ultimately, the number of unique subproblems here is in terms of a polynomial. But the total number of subproblems are exponential. So if I want to write it down, so for factorial, using DP, there are two observations. One is the number of total, or say total number of subproblems. So this is in terms of something n to the power n, which is n factorial, to be very precise. But number of, say, unique, absolutely, there will be an increase. I've told you, there will be an increase in the auxiliary memory space. But will it really affect if I'm getting an exponential advantage with respect to my time complexity? That is something that we want to notice here. So, but number of unique subproblems with DP using factorial, using DP for factorial will be ultimately the space that I am using for the auxiliary memory. That is nothing but the number of unique subproblems. So using this, I can call that if I am allowed to put auxiliary memory space, then ultimately my time complexity using dynamic programming for factorial will be, or can be, big of n using, say, I'm just writing it, say, a clever approach or the best known approach. Now, whenever we have known an approach or a paradigm, our target is to apply to TSP. Now, let us see if TSP using DP can be of any good help or not. So, generally, I'll not go into the depth of the algorithm level. I'll not go till that level. But generally, the problem of TSP is, say, I have only 4 vertices. Let me start with 4 vertices itself. Okay. What are the cost and all? I'm not going into that. Because why? Because here, I want to map it to the complexity classes. I'm only interested to know that what are the unique subproblems here, not anything else on that. Okay. So say I have 4 vertices, 1, 2, 3, and 4, where 1 is my source vertex, 2, 3, and 4 are my remaining vertices. So it is a set. Let me write it in curly braces. So my target is that from starting from 1, I have to cover 2, 3, 4 in any order that is not yet defined to me, but ultimately again I have to come back to my original vertex. So the mathematical recursive like definition I'm not writing here, but ultimately it works something like that. If you follow it, you will be understanding it. So this is nothing but, so cost of this reaching to 1 to 2. Now the concept is I can pick up any of these vertices as my immediate next vertex after 1. So either I can take 2, that is 1 to 2, or I can take 3, that's 1 to 3, or I can take 4, that is 1 to 4. I can pick up any one of them. Now, once I pick up, so I'm not writing the cost, but let me write the solution space in that case, how it will look like. So then it will be like, say I have picked up 2. So 2 when picked up and 3, 4 will look something like that. Next, I can either take 2 to 3, then it will be, if I pick up 3, then what is the condition of 4? Or it will be 2 to 4, cost of 2 to 4, which is a direct cost, plus TSP. If I pick up 4 after 2, then the remaining vertex I have to cover is 3. Or remaining set of vertices that I have to cover is 3. Similarly, this is case number 1. So similarly, if I cover, say, I have after 1 I have picked up vertex number 3. So if I pick up 3, the remaining vertices will be 2 and 4. And this is nothing but cost of 3 to 2 plus TSP. If I pick up after 3, 1, 2, 3, then I pick up 2. So I am left with only 4 that I have to cover. Or it will be cost of 3 to 4. Plus, if I pick up now after 3, if I pick up 4, so it will be 4 I have picked up or selected, then 2 is only remain. So are you getting it? It's all about a few possible choices, but all choices will come under the brute force and also come under DP. Only benefit is our aim is to find the number of repeating subproblems. Okay? That is only the advantage that DP can provide. So now with that concept, if I draw this thing, I hope now you will be able to map it. So it's kind of that. I'm not writing the 1 to 2 cost part. I'm just writing the recursive function call, so which will be either TSP, then 2, 3, 4, or it will be TSP 3, then 2, 4, or it will be directly TSP 4 and 2, 3. Right? Only I'm writing the recursive part. Okay. So this part again will be like 3 has been, let me assume 3 is chosen. So 3 to 4, or it will be TSP 4, then 3. Then this one will be TSP 2, 4. And this one will be TSP 4, 2. And similarly, this one will be TSP 2, 3. And this one will be TSP 3, 2. Okay. Now here again considering that 4 is the only one, so 4 is chosen. So if I choose 4, I will be left with only a null thing, null vertex, okay, which is nothing. So similarly here also it will be TSP 3 epsilon, TSP 4 epsilon, TSP 2 epsilon, TSP 3 epsilon, and this one is TSP 2 epsilon. So if you notice very carefully, now I have to end here because this one nothing, this one is nothing but the direct cost of 4 to 1. Similarly, this is nothing but the cost of going to directly 3 to 1. So this is just the end one. Automatically, it will imply or it will be somehow hardwired into the code that TSP 4 epsilon means that from 4 I have to go back to the source vertex 1. So this one is also 2 to 1. This one is also cost of 3 to 1. This one again is cost of 2 to 1. So ignoring the cost part, only following the recursive function or the subproblem calling. If you see, this is a unique subproblem. For this problem, I want to call. So this is the main problem, right? Now I want to find the subproblems which are unique. This one is 1. This is another subproblem unique. This one. Is there any repetition of TSP 3 and 4? Nothing like that. So 4, 5. This is also unique. This is unique. Also, you do a double check. This one is a 7 and this one is, I guess, 8. Then this is 9. This one is 10. Okay, 4 and 3 epsilon is covered. Now see, this one is a repetition. So let me mark this one. I will not take into account this one because 4 epsilon is already there. Unique one, 2 epsilon is the new one. So let me again take it. Okay. Then it is any problem that I'm like missing. 1, 2, 3, then 4, 5. Yes, this one. Sorry. So this is another one. I skipped this one. So this will be, I guess, 12. I just missed this 8. Sorry. So this is say 7. This is 8, 9, and accordingly it will be ultimately 12. because 3 and epsilon is also repetition. This one you can see, this is a repetition. Similarly, 3 epsilon is another repetition. Similarly, 2 epsilon is another repetition. So just notice here that is the number of unique subproblems for n equals to 4, that is 4 vertices, is nothing but what? It is 12. Okay. Now let me take another example. We want to understand it even more. Say for example, I have a case like TSP 1, then 2, 3, 4, 5. It's a very like naive example. Only 5 cities is not at all a realistic case. So let me have this thing. Let me draw it. So this is nothing but TSP, then 2, 3, 4, 5. How many possible cases will be there? Since I have 4 vertices in the set, so there will be 4 edges. Simple. So TSP, this one, then 3 will be chosen, 2, 4, 5 are remaining. Then TSP, 4 will be chosen, then 2, 3, 5 is remaining. Then TSP, I guess 5 will be chosen, then 2, 3, 4 are remaining. So from this one also there will be 3 edges because 3 vertices. What will be there? So this is TSP 3, then 4, 5. This is TSP 4, then 3, 5. And this one is TSP 5, then 3, 4. Similarly, here also 3 edges will be there. So TSP 2 and 4, 5. TSP 4 and 2, 5. Okay. And yes. And TSP 5 and 2, 4. Similarly, from here, 3 cases. Just it will be 2, then 3, 5. Then TSP 3, 2, 5. Then it is TSP 5, 2, 3. And similarly from here, let me write just it in this way. So it is T or TSP 2. Just check till now, is there any repetition or not? So 3, 2, 4 and TSP 4, 2, 3. Okay. Now this one again will be 2 things. TSP 4, 5 and TSP 5, 4. Now I will not write the TSP thing so many times, so I'll be directly writing it. So this is 3, 5 and this is 5, 3. So this is 3, 4, this is 4, 3. This is 4, 5. Let me write it in a bracket form. Keep on checking with the repetitions. So this is 5, 4. This is 2, 5. This is 5, 2. This one is, I guess, this is, okay. This is 2, 5 and this is 5, 2. So this is 2, 4 and next one is 4, 2. This one will be 3, 5 and 5, 3. This is 2, 5. Okay. Uh, uh, this is 5, 2. I don't have that much of space. So this is, say, let me write here. So in 2 branches, I'm writing here. Okay. So this is 2, 3 and then 3, 2. Similarly, this will be 3, 4 and 4, 3. Then 2, 4 and 4, 2. Then 2, 3 and 3, 2. Okay. This is 5 epsilon. This is 4 epsilon. So this there is only one mapping. So 5 epsilon, 3 epsilon, 4 epsilon, 3 epsilon, again 5 epsilon, again 4 epsilon. This is 5 epsilon. This is 2 epsilon, 4 epsilon. This one is 2 epsilon. So this is 5 epsilon. This is 3 epsilon. Okay. I have 4 remaining. So they will be, I'm just writing in this way. Okay. For all these values. So this is 5, 2, 3, 2. So 5 epsilon, 2 epsilon, 3 epsilon, and 2 epsilon. Similarly, this will be 4 epsilon, then 3 epsilon, then 4 epsilon, then 2 epsilon. There is 3 epsilon, and there is 2 epsilon. Now we are in. Okay, this is the end of the entire search space. So these are the total number of subproblems that we have for TSP. Okay. Now our target is, since we have allowed or we have the provision to use or remove or only calculate the unique subproblem, let us start with that. So this is the main problem. So this is the first subproblem, second one, third one, and the fourth one. Calculate and tell me if I am again, like, I'm picking up two cases, if there is any repetition. Okay, just tell me that. So this is the fifth one, sixth one, and seventh one. This is 8th, 9th, 10th. This one is 11, 12, 13. Okay, so if this is 13, so this is 14. This one is 15. This one is 16. Till 16, there is definitely not any repetition. So next is this thing. So 17, 4, 5. Okay, let me know if there is any 4, 5. Okay, from this last part, you should be a bit more cautious. So 5, 4 is not a repetition. 3, 5 is not yet a repetition. 5, 3, no repetition. 3, 4, not yet any repetition. 4, 3, no repetition. 4, 5, it's a repetition, so ignore it. 5, 4, it's also a repetition. 2, 5, not yet any repetition, so let me take it. 5, 2, not yet any repetition, let me take it. 2, 4, not yet any repetition, let me take it. 4, 2, also no repetition yet. Okay, 2, 6. 3, 5, it's a repetition. 5, 3, repetition. 2, 5, 2, 5, yes, it's also a repetition. 5, 2 is a repetition. 2, 3, is it yet a repetition? No. So I have till 26. So 2, 3 will be 27. 3, 2, not yet any repetition, so it will be 28. Now it's 3, 4. 3, 4 is already repetition, cancel it. 4, 3 is a repetition, definitely cancel it. 2, 4, 2, 4. 2, 4 is already taken, so cancel it. 4, 2 also. 2, 3, here I have taken it, so cancel it. And 3, 2 also cancel it. So far I have till 28th. Now 5 epsilon is a new subproblem, right? So it is unique. So count it. 4 epsilon, new one. Haven't ever encountered this thing. 5 epsilon, yes, it's a repetition, cancel it. 3 epsilon is a new one, take it. 4 epsilon repetition, 3 epsilon repetition, 5 epsilon repetition, 4 epsilon repetition, 5 epsilon repetition, 2 epsilon is a new one that I am encountering. So 3, 2, 4 epsilon is a repetition. Again, here it's a 2 epsilon repetition, 5 epsilon, also repetition, 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 and repetition. So here is the end. So you can see a lot of states are getting cancelled out. That is true. But despite of that, whereas I was during the factorial, when I was trying to calculate factorial of 4, in classical it was 24. Okay, without DP. But with DP it was only 4. For factorial of 5, in classical without DP, it was 5 factorial, that is 120. But in this thing, like say with DP, factorial of 5, it was only 5. So you can see there is some advantage that we are getting. But what about here? For n equals to 5 cities, so only for 5 cities, if I have to find Hamiltonian cycle using TSP, which is a basic or a primary problem for supply chain optimization, logistics. A lot of industries are there which incorporate this TSP. So it's a very like a fundamental optimization problem that we have to deal with. So with only 5 cities, how many unique subproblems I have? So number of unique subproblems, that is 32, which is quite high. Now, considering you have understood till this part and why it is number of unique subproblems and why ultimately it is giving you this much of complexity. Okay, Next is bit of analysis. I'm just claiming something, then I will prove it. What if I tell you that for n cities in TSP, the number of unique subproblems is nothing but n minus 1 into 2 to the power of n minus 2. Whether this is correct or not, we will prove it. Okay. But say, just put the value. Say n equals to 3, only 3 cities. So what is the value? Say unique subproblems. I want to calculate USP. So it will be 3 minus 1, that is 2 into 2 to the power 3 minus 2. That is 2 into basically 2. That is 4. Number of unique subproblems. Pretty less, not to worry. N equals to 4, we have seen that it is basically 12. We also have seen that, right? But if it is equals to 5, the number of unique subproblems is basically 32. Pretty much of a kind of a something which is quite a bit more gap. If it is n equals to 6, number of unique subproblems will be, just put the value here, so it will be 6 minus 1, that is 5 into 2 to the power 4. So it's 5 into 2 to the power 4. So that is 5 into 16, that is 80. So from 32, now it is 80. Okay. Now if it is n equals to 7, the unique subproblem will be 7 minus 1, that is 6 into 2 to the power 7 minus 2, that is 5. So it's 6 into 32. It is nothing but kind of this. So you can see it's 4. From 4 it is 12. From 12 to 32, 32 to 80, 80 to 192, which is significant, quite a number of increase kind of thing. So definitely the graph is going to be not really, maybe not extreme polynomial, but it is also going to be very high. There is no really, so therefore the conclusion is even with DP, there is no significant advantage we are getting. That is why the optimization version, not the decision version. Now we should be knowing what's the decision version of a problem, same problem, and what is the optimization version of that same problem. So that is why the optimization version of TSP is known as a NP hard problem. Now, I'm going to give you a quick mathematical proof for this thing. We'll see actually that how to derive this till this part. So proof is for the number of unique subproblems for TSP, which is n minus 1 into 2 to the power n minus 2, which will finally lead to the time complexity. Okay. So say n is the total number of vertices or cities, including the fixed starting vertex. So including source. Therefore, remaining vertices count is what? N minus 1. No issue. Okay. So each subproblem is defined as, subproblem means in the graph, the way we written it, TSP, say U, then mask. Mask is nothing but, you can write it anything, that is not a something. So mask is a subset of 2 to 3 to till n. 1 I already have taken in U, so mask is a remaining. Okay, why here I have not written 2 to 3, 2, 3, 4 till n, because it can be, if I pick up 3, it will be remaining vertices. So likewise, it's better to write it in a abstract function, like variable name, which is say mask, which denotes the subset of 2 to 3 to till n. Okay. and U belongs to mask. It is the last visited vertex. To fulfill the Hamiltonian cycle criteria. And we want to count the valid pairs of that. Okay. Let's denote. Let us denote. Say M is equals to n minus 1, excluding the source node. We want to count all pairs of U and mask. That is our target. So their count we want to find. Okay. So say for each subset of size, say K, there exists MCK. You should be knowing this. This means from M I am choosing CK. So this is an alternate representation. We can write it MK in this way. So this many subsets, and for each subset, if you want a map, just see how many edges and how the number of vertices within the subset is getting reduced as we move on. For the n equal to 4 and 5 vertices, then we will understand it. That's why I first have given you the example rather than the mathematical notations. And for each subset, there are k choices for your Q. Okay. Then how many total subproblems will be there? Therefore, total number of subproblems will be sigma k equals to n1 to m, then mck times k. Now, what is mck? So, mck is nothing but m factorial divided by k factorial into m minus k factorial. From the basic definition of combination, we know that. So, from this, if I just say multiply k into mck, then it will be m factorial divided by, so k is nothing, k factorial is k into k minus 1 factorial, k and k will be cancelled out, so it will be ultimately k minus 1 factorial into m minus k factorial. So this I can write it down in this way, that is m into m minus 1 factorial. M factorial can be written in this way, divided by k minus 1 factorial times m minus k factorial. So now you understand that it is nothing but, it can also be thought of in this way, that it is nothing but m into m minus 1 factorial divided by k minus 1 factorial times this m minus k factorial can be written as m minus 1 minus this k minus 1. Just check it. If you cancel it out, so it will be m minus 1 minus k plus 1 plus 1 minus 1 will be cancelled out. So I can write it down in this way. Why I'm writing it? Because I want to write it in the form of m minus 1 c k minus 1. So then it will be, so m into this entire part, now I can club it together and it will be m minus 1 c k minus 1. Okay. Therefore, applying the sum, it will be S is equals to, S was initially k equals to 1 to m, then it was k into mk. So this thing, which we already calculated, so this will be sigma m into m minus 1 k minus 1 with the same variable. We have already proved that this k into m minus k is nothing but m into m minus 1 k minus 1. Let's some algebraic calculations. So considering that, we can write it down, because m is not a function of k. So if I just write separately this one, it will be k equals to 1 to m, then m minus 1 k minus 1. Now from this one, I will be putting k minus 1 is equals to j. Okay. So initial value was, let me write it. So it was m into, so from it was m into sigma k equals to 1 to m minus 1, k minus 1. If I just write, say k minus 1 is equals to j, then for k equal to 1, j will be equals to 0, and if k is equals to m, j will be nothing but this thing, m minus 1. Therefore, this was s, so s can be rewritten as, I can write it down as m, and this will be, it was from k equal to 1 to m. So right now it will be, I have replaced k with j, so it's a j equal to 0 to m minus 1 c j. Yes, yes, sorry. So k equal to 1 to m will now be j equals to 0 to m minus 1. Okay. Now this is a binomial expansion. So from binomial expansion, coefficients, we know that if it is x plus y to the power n, then it is x to the power n plus nc1 into x to the power n minus 1 into y to the power 1 plus nc2 into x to the power n minus 2 into y to the power 2, likewise, till it is y to the power n. So the general formula is nothing but this thing, k equal to 0 to n, say nck x to the power n minus k into y to the power k. That is the general form, right? Now similarly, if here we think that it is x equals to 1 and y equals to 1, I put it, then it will be ultimately here 1 plus 1 to the power n, that is 2 to the power n. So 2 to the power n is nothing but, this entire thing is sigma k equal to 0 to n, then it's nck into 1 to the power, basically something which is into 1 to the power something. So 1 to the power anything is ultimately 1, so it is nothing but this. So this is nc0 plus nc1, likewise still ncn. And we also know that total number of subsets of a set consisting of n variables is nothing but 2 to the power n, which also comes from this concept that out of the n vertical variables, what either I can choose nothing, that is 0, or I can choose 1 or 2 or 3, likewise maximum I can choose all the n vertices. So this is the same theory. Now here, if in case of n, if I put m minus 1, then how it will look like is, in place of n, I will be putting m minus 1. So now by setting, instead of n, I will be putting m minus 1. So the earlier equation, here I will be putting m minus 1. So it will be m minus 1. And instead of k, let me rewrite it with the symbol j. So now k will be replaced by the symbol j. So if I do that, it will look something like that. So then it's, instead of k, I'm writing j equal to 0 to n will now be replaced by m minus 1. So it will be this thing. And this was what it was, like k. So now it will be m minus 1 c j. So if you notice, it is the same thing that I have got here. Okay. So this will be nothing but 2 to the power m minus 1. Right? Now, your sum was s equals to, if you see here, sum was s equals to m into this entire thing. So that means now your sum will be m into 2 to the power m minus 1. What was your m? So n was equals to m minus 1, therefore n minus 1 was your m. So replacing it with n, where n minus 1 is equals to m basically. from this thing I'm writing. So it will be m, instead of m, just write it will be n minus 1. And 2 to the power m will be now n minus 1, which is n minus 1 into 2 to the power n minus 2. So if you notice, this was your number of unique subproblems where we started with. So here we are proving that the space complexity, so number of unique subproblems, number of unique subproblems, okay, number of unique subproblems will be n minus 1 into 2 to the power n minus 2, which is nothing but the space complexity. So it belongs to the class of n into 2 to the power n. It is 2 to the power n by 4. So all these things will be cancelled out. And the number of time complexity is nothing but we go up. This is for one vertex. When I'm starting with one vertex, now I can choose any one of the vertices as my initial vertex. So it is nc1 into your n into 2 to the power n, which is big O of, or belongs to big O of n square into 2 to the power n. So now your n factorial has come down to n square into 2 to the power n using dynamic program. Okay. Yes. Therefore, so where we started the discussion is started with this thing. So m is equals to n minus 1. Yes. Sorry. Just one variable. There is a mistake. We started with this thing. So m is equals to n minus 1. Since I've taken two variable names same, there was a confusion here. It is not from this one. This is for the general one. So since I have taken here, after I got this thing, s equals to m into 2 to the power m minus 1. Since I have taken that m is equals to n minus 1, it started with that notation that the number of remaining vertices was n minus 1, which was denoted by the symbol n, denoted by the symbol m. So here it will be a simple replacement. It's a m was your n minus 1. So directly, so m minus 1 will be n minus 2. Likewise, these two substitutions I have done here. Since I have taken the two variable names same, there was a confusion in this line. Just ignore these two. So this will be the as per the convention. What we have selected is, we instead of writing always n minus 1 like that, we have chosen that the number of remaining vertices out of n was m, which was n minus 1. Accordingly, if you solve it, so you are getting the number of unique subproblem is n minus 1 into 2 to the power n minus 2, which is a subset of the complexity class n into 2 to the power n, but this is the space complexity. Since this is coming with respect to only the one vertex, now it can be also like any number of vertices you can start with. So out of n possible vertices, you have to choose any one. So it is nc1 into your number of unique subproblems. So it's n into 2 to the power n, which is n square into 2 to the power n. But despite of that, you can notice one thing, because of this particular factor in the time complexity, where n or a polynomial of n is in exponent, it is still a hard function. And it is a NP-hard problem. Is it clear till this part? Is it absolutely clear what I covered till now? Thank you. Others? Anyone has any question? Any step that you have any doubt? Okay. Great. Great. Thank you. Okay. What is the time now? It's 2:55. Let us take a small break. This was a bit of a rigorous proof and all this stuff. Just take a small break. Then I will start with the remaining half. I will start with the quantum complexity. I hope that is okay. So we'll exactly start from 3 and we'll cover till the topic ends. Okay. Great. Okay. So we will all meet at 3. Thank you. Yes, yes. Let us start. Let us start. Okay. Till this part, it's okay. Someone who has typed that whether you mask. I hope you have understood the concept that mask was a remaining set of vertices. If there is any convention or any notation you find that that is not matching, so just accordingly adjust. The concept is pretty easy, or whatever you have got, that is the thing. If you see some variable, because a lot of variables I have taken, so if there is any typo, please consider that. Whatever logically should be like coming true, that will be true. Is it? That's it. Okay. So now from this thing, from this thing, just a quick story or a quick recap I want to give. So initially we started with the class, where we have seen that it's a probabilistic, it's a polynomial time solvable by a deterministic Turing machine. Then we have seen the NP, which is a polynomial time verifiable by a deterministic Turing machine, or for solve it is a non-deterministic Turing machine. So the NP thing was non-deterministic polynomial time. So if we give a non-deterministic polynomial, non-deterministic Turing machine or NDTM, it will be solvable in a polynomial time. But if since we have a deterministic Turing machine, so it takes a non-polynomial time or an exponential time, right? So non-polynomial is kind of where in the exponent is either n or n square, or it's a polynomial of n. But the polynomial of n itself is in exponent. So it is kind of that. So it's kind of something. Here it's a poly of n. This is kind of a notation for, or say, in this way also you can think it of, where it can be either n or n square or root over of n or anything like that. It's a function of it. So then we have seen that there is a concept of NP-hard, where we believe that if one problem from NP-hard set, or it is believed that that a problem will be NP-hard if for all problems that are in NP is polynomial time reducible to that problem. Then that new problem will be called an NP-hard problem. So it is as hard as any of the NP problems. And the next fourth one was the NP complete problem, where we have seen that that problem itself has to be in NP. So it's an NP hard problem where the problem itself is at least as hard as all the NP problems, but it is also verifiable in polynomial type. Okay, then that problem is known as an NP complete problem. So, but all these things are based on a deterministic Turing machine. That is why we are using polynomial and non-polynomial. But deterministic model has definitely some sort of disadvantage. So deterministic one, from the deterministic computation, deterministic model of computation, there is a fine transition to some of the advanced versions where we use some sort of randomness concept, randomness criteria, randomness in computation. Okay, so these are now some probabilistic model, but classical probabilistic model. So they are based on some classical randomness model, computing model or computation model. So these are called probabilistic, or say classical probabilistic complexity classes. Okay. So their purpose was that for the problems like TSP and something, can we really go for some solution where we will be using some randomness, or it's kind of an approximation, where we will verify maybe the correct answer with a very significantly high amount of probability. So maybe it's not a very definite model, but it is probabilistically very high model if it has to accept that particular language that will belong to this complexity class. So it's kind of a probabilistically high or a probabilistically low computing model concept is used in order to accept or in order to set the membership thing, that whether that problem belongs to this complexity class or not. So again, I'm telling it's not quantum. It's not quantum randomness, but it is a classical randomness. So it's kind of an intermediate version between the classical deterministic versions and the quantum versions or the quantum complexity classes. So here the concept is there are two different models that belong to the probabilistic complexity class. What are they? They are BPP, which is also known as bounded error, probabilistic. We'll understand each word. Okay, don't worry. Bounded error, probabilistic, polynomial time, complexity class. And the second one is only PP, which is a probabilistic polynomial time. So from the terms, you will understand one thing, that there are two different things that we should be understanding, because we know already what is a polynomial time. Okay. So now next, what we should be understanding is what do I mean by a bounded error and unbounded error? What is that concept? Second one is, what is the concept of a probabilistic polynomial time thing? What do I mean by that? So on that note, first is this thing, that is the bounded error. Bounded error. Now this concept is that algorithm, say, it has certain either a correct solution or an incorrect solution. But with bounded error, we believe that the probability of incorrect outcome or computation is strictly very less than half. To be very precise, it is even less than or equals to, say, 1/3 or 1/4. What is the first point? That is, it is bounded, that how much of an error in the outcome or the machine can say, there is a flaws in the machine, whatever you say, that I want to consider, that error probability is really really like it has certain kind of a boundary. It's constricted. So the thing is that the first point for bounded error is the probability of incorrect outcome. Probability of incorrect, say, computation or outcome, whatever you say, that is strictly less than half. Okay. Is my audio perfect? One has said no audio. Is it perfect to others? Okay. Thank you. Thank you. Please rejoin. Please rejoin then. Okay. So the bounded error is the probability. The first point is the probability of incorrect computation is strictly less than half. To be very precise, or to be precisely, it is less than equals to 1/3 or less than equals to 1/4, kind of that. Any model I can choose. There is no definite value, but the concept is it has to be very less than the 50% probability case. Understand the intuition? It's a classical randomness model where we are just predicting based on that what expected outcome we are getting. How much of the best outcome or how many possible outcomes have to take in order to get the correct result, right? Okay. The second point is the machine means a Turing machine. The machine must accept the outcome with high probability of correctness. That is, if I say that I have a correct solution, that has to be significantly very high, at least 80%, 85%, nothing, something like that. Okay, so one third, less than one third should be my chance of giving an incorrect solution. And of course, 1 minus one third is two thirds. So it means that greater equals to two thirds should be my, at least my correction or say correct outcome giving probability. Okay. Third one is the repeatability. So repeatability means that by repeating a computation few times and by taking the outcome, okay, then taking the outcome in terms of the majority. Then looking for the majority, we can reduce the error contained probability. And to what extent? To exponential extent. Why exponential? Because after every measurement, it will ultimately, the error will be minimized because the success rate will be maximized. That is the theory of repeatability. Okay. So the concept is, by repeating the computation, say, for example, if I am telling that in first case, I have 30% of a error chance, so which will be 0.3. So next one will be into 0.3. So that is 0.09. Now you can imagine that it is ultimately your error chances are getting minimized. And how much? To what extent? Exponentially. Okay. So by repeating the computation a few times, and then by taking a majority vote, we can reduce the probability of error exponentially. Say first measurement, that is 0.3. Second measurement is 0.3 into 0.3, that is 0.09. So this is 30% probability. This is 9% probability. So third measurement, by taking the majority vote, it will be 0.3 into 0.3, that is 0.09 into 0.3. So this is 1, 2, 3. So 0.027. So this is nothing but 2.7% probability. So these are our error probabilities. So this is probability of error in first. This is error in second because there is a dependent event. And this is error for third case. So by repeating it, I can actually reduce it from 30% to 9% to 2.7%. So your error ultimately is somehow bounded. That is the theory of a bounded error. Okay. So definition wise, the BPP is an algorithm will be correct on every input with probability at least two-thirds. And this is big enough. It's not exactly, it is at least, so you can understand it's greater equals to, but there is no precise value that it has to be 0.6667 or something like that, but it has to be really big enough to give some statistical evidence. And this concept is mostly used in RNGs or random number generators. Precisely the pseudo RNGs. Okay. So this is the thing. For an example, if I have to say, say a language, say for language L belonging to the class BPP, if X belongs to L, then probability that machine accepting the language X will be equals to 1, that it will accept, is greater or equals to 2/3. And if X does not belongs to L, then the probability that the machine, when given the language X, will accept it, that is, this is an error thing, so the error probability will be less than equal to 1/3. Okay. So an example is, say L is a language. L is a language that's kind of working this way. So it accepts a set of all strings that are considered yes instances. Say L is a all prime numbers written in binary. Okay. Then say 101, which is for binary form of 5, decimal 5, is in L because it is a prime number. But 110 is not in L, which is 6. Okay. So now say M is the probabilistic Turing machine. If M is a probabilistic Turing machine, it decides whether an input X belongs to L or not by flipping, say, random coins. Each coin flip will be ultimately giving you that what is the outcome that you are getting. Okay. And probability of this mx equals to 1 means that it is the probability that machine M outputs accept when given the input X. Therefore, X belongs to L, meaning the yes instance, so it is to be accepted. Okay. Therefore, M must accept X with at least 2/3 probability if X belongs to L, that is the yes instance. Okay. Now, another one was your unbounded error thing, which was PP, which is probabilistic polynomial type, or also known as unbounded error. Not exactly unbounded error, but yes, it's better to write not bounded error. Probabilistic polynomial. So this category is pretty much similar to this one, this BPP. Only in definition, there is a fundamental difference that here we believe that there should not be very tiny gap in the error analysis. That is whether if it accepts, then also it can have just a probability of more than half. So that means if it does not accept, that also will be having some probability which is very similar or near approximation to the yes probability. So it's also like less than equals to half if it is not to be accepted. If it is to be accepted, it will be greater than half. Okay. Now you will ask that in what cases, why really we need this kind of solution, considering it has certain chances of error. We will come to that point. So the thing is, it is a class of problems, or say probabilistic problem, whatever you say, problems. It is solvable in polynomial time by a probabilistic Turing machine with some unbounded error. Meaning that we do not have any provision to tackle the error in a significant sense. Let me write it. We do not have or don't have the provision to tackle the error probability in a significant way. So I've told that for BPP we need it, and one of the application are pseudo random number generators, and they need to have some statistical evidence. So in pseudo random number generator, in order to get certain outcomes, or once we got certain outcomes of random bits, we often pass it through some statistical tests. So there, in order to validate that data, we have to go for the BPP model, where we ultimately aim for getting or finding that whether my error content, as we move forward, like as we keep on increasing the number of more random bits are introduced into the bit stream, say, whether the chances of error is getting minimized or not. Now, error, that is very contextual. That depends on what I define as my problem, to consider it to be an error or not an error. That is contextual. That depends on what I give it as an input. There is a problem instance. But depending on the problem instance, whenever more bits are introduced, the chances of error should be minimized. That is the concept of BPP. So, and in random number generator for statistical test, that has an application. But for PP, it is a significant way. That means that it will correct on every input with some probability greater equals to half. So the definition wise, it is something like that. It is the same thing as we were writing there. So probability that mx equals to 1 for x belongings to L will be greater equals to half, and the probability of mx equals to 1 for x does not belong into L will be less than or equals to, say, half. So one thing you can observe, it's kind of a 50% or somewhere maybe 51 or 50.6%. Okay. And at least that limit is permissible. We can definitely go for further level, but it does not guarantee that there will be a significant difference. And here also maybe it is somewhere like, say here it is 50%, so it will be, say, 49 point some percent. Something like that. It's just less than this. This is what I want to be. And this way it can proceed, and here also this way it can be more, and this way it can be less. But only case is that it is not guaranteed. So there, that is why we called it an unbounded error, or not really bounded error. Okay. So if I have to draw a diagram in order to describe it, so BPP and this PP, where it is a bounded error probabilistic polynomial time, and probabilistic polynomial time with an unbounded error, if I say it, so it will be a subset of that, where definitely PPP is kind of, it follows a larger gap between the correct and incorrect. correct and incorrect. And here is a concept of bounded error and majority voting. Unlike BPP, here there is a very tiny gap. And here, very important point is amplification of success is possible through repetition. In what way success is possible? By diminishing the error probability. Or error containment in successive measurements. On the contrary, here it is a very tiny gap between correct and incorrect. And amplification through repetition is also very less possible. Repetition possibility is less. Both for success and fail, it should be one case it is greater than greater than equals to two-third and less than equals to two-third. Considering both, it cannot be exactly equal. Okay, it just a cases, at least there is at least thing. So there is a range, but mostly it can be either two-third and one-third for BPP. And for PP, for mx equals to 1, if x belongs to L, will be greater than equals to half. And if it is less than or if it does not belong to L, then mx is equals to 1 will be less than equals to half. Okay, so given a Boolean formula, so one application here, it is like pseudo RNG. And here one application can be where we aim for having a like say Boolean formula where we see that whether more than half of the solutions satisfy the Boolean expression or not. So it's given a Boolean formula does more than half of the solutions satisfy the expression or not. These are a few cases where we keep it in this thing, PP, polynomial, probabilistic polynomial, and otherwise we put it in the BPP. And BPP, one example, you can also see it in form of in the whenever we will do the quantum analog, I will describe it. Yes. So this is the one. Now, exactly where BPP ends, quantum thing is introduced, where we believe that instead of it being a probabilistic polynomial, it will be now a quantum polynomial. So bounded error, quantum polynomial time complexity case, which is exactly the classical analog of subset of P class or something else. Yes. So P can be thought of somewhere belonging to this. So it's kind of some advancements that we are getting. So PPP definitely will belong to this thing, PP. P also we can think in this way. Okay. So now as we were discussing, so from classical or which was deterministic model, we are now coming to classical or say randomness or classical probabilistic model. Probabilistic model. Next one is, here comes the P, NP, NP hard, NP complete, these ones. Here it is like BPP and PP. The next one was a quantum polynomial time model. So here, unlike classical randomness, here it believes on quantum randomness. What's a quantum itself? Yes, approach. Okay. So for that, you have seen what BPP is. So we will start with this thing with its quantum analog, which is BQP, which is bounded error quantum polynomial type. Bounded error quantum polynomial type. Let me write the definition first, then I will tell you that how it really differs with BPP, though the definition wise it looks quite same, and we already have seen this thing while we were doing the quantum computing stuffs, but how they are related. I will do that mapping. So say a language L belongs to the new class of BQP. Now, if there exists a quantum Turing machine or QTM, which is nothing but equivalently, you can think it of as quantum Turing machine. Let me write Turing machine. Turing machine is an abstract computing model. In quantum, or how we compute is a quantum computing model, which is nothing but a quantum circuit model of computation as we are doing. So it's nothing but generally a quantum circuit. So what a quantum circuit is, as we have seen it, its equivalently is mapped to the quantum Turing machine. Okay. So quantum circuit, say Q, there exists a QTM, say Q, such that for all x belonging to L, the language L, the probability that the circuit will accept this thing and with this probability will be greater than equals to 2/3, exactly the same as BPP. And for all x that does not belong to L, the probability that this thing will be equals to 1 will be less than equals to 1/3. So it's just the same, rather in the lights of quantum version. So just like BPP, it uses some sort of quantum randomness. So we know what are the components of quantum randomness, that is, or how we bring it. So postulate wise, it's just the superposition, entanglement, interference, decoherence, all those stuffs. So it's exactly the same. Those are the kind of elements for that. So it will be using all these kind of quantum randomness instead of classical probabilistic randomness. Target is to check whether a quantum circuit, which is nothing but a quantum Turing machine, accepts it or not. Okay. And in order to accept it or not means what? Means if it is a quantum circuit, how will we know that whether it is accepting something as per the way we want it or not? The quantum circuit is nothing but a combination of quantum gates, right? So now we'll try to analyze a bit more on the QTM, which is nothing but a quantum circuit. So we know that quantum circuit follows is nothing but it's something looks like this. This is already the way we have seen it. So something like that, all this stuff, right? So this is how a quantum circuit is. Now, what do I mean by whether it accepts a particular language that or say particular input that belonging to the language L or not? How we do that? So quantum circuit is nothing but some sequence of quantum gates, and applying all of them are known as the, what does it known as? An unitary operator. So the concept is now we already know, and just like BPP, just like bounded polynomial, probabilistic polynomial, BQP uses quantum randomness instead of randomness, which is this theory like superposition, entanglement, decoherence, and all those stuff, interference, all those stuff. Okay, instead of coin toss in classical randomness. And how the verification or how the checking is done? It starts with this. Now, since you can see the arbitrary quantum circuit, a small quantum circuit that I have drawn. So initially what you need for this, you have to start with an input register. So let us start with it. So if we have some input register, say it is get X, okay, we will be doing some, apply some unitary circuit or unitary operator, whatever you say. So we will be applying unitary circuit, which is nothing but a set of quantum gates. Now, once I have applied all of them, I will then measure the quantum state. Better to write, measure the time evolved quantum state. We have seen it, I guess, in last class. What is the time evolution of quantum states and all through Schrodinger and Hamiltonian. So this is the time evolved quantum state we will be measuring. Then we will be checking at what kind of an output we are getting, whether we are getting 0 or we are getting 1. Now, depending on whatever is there, as you have to accept it, depending on that, what I choose, that if I want say 0, then the 0 occurrence probability should be greater or equals to 2/3, as you can see in the definition. And if I give you 1, so Qx equals to 1 does not mean that output will be equals to 0 or 1. It is just the case that determines that it is an yes instance. So Qx equals to 1 is a significant signifier of a yes instance. So if I say that output 0 should be coming with 70% probability, then that means it will satisfy the big QP problem. Because for that particular, say, output, your quantum circuit or the possibility or the probability of getting the outcome 0, which is equals to XA, for the quantum circuit Q, will give you an yes instance, that is Q of X will be equals to 1, and that probability is 70%, and 70% is nothing but 0.7, which is greater equals to the 0.6667 criteria. So that means that language will belong to the BQP class. So it is like that. Are you getting it? And vice versa, if it is like say output 1 you want to get, then the one output getting concept is known as your ES instance. That it has to be, say, 60% probability that you are getting. The outcome probability that you are getting is 60%. So in that case, it will ultimately yield something where the probability that Qx is equals to 1 after all your unitary operator, that should be less than equals to 1/3. So that means if your 1 and it is not the desired one, and that is if coming 60% means there is an error, because it should be less than 1/3 to be undetected. Otherwise, that is something that is there is something wrong in the unitary operator. Okay, so that is okay. So on that note, that means yes. So that means say for X belonging to L, there is no as such specific reason, but it is at least say more than 1 after half or 50-50%. The immediate next is 1/3. So at least we believe that if it is 2/3 and 1/3, then after significant measurements, it will be ultimately more. And those of you who remember or if you know, or if you have attended the QT-01, there we covered the Grover's algorithm. And through multiple iterations, we have seen that how we can actually go towards our desired state. So that process was amplitude amplification. So it is kind of the same concept. It is kind of the same concept, so that our ultimate quantum circuit works in the BQP model and accepts the state with the significantly high amount of probabilistic amplitude and probability itself. So Grover's algorithm, Shor's algorithm, all these are like prime examples for the BQP technique. Okay. So for X belongings to L, the final measurement state, gives one with probability greater or equals to 2/3. And I've shown to you that why it is. You can of course choose some other value. You can take it like more than 80%. That is absolutely okay. Or 0.8. Okay. This is a minimum criteria because it leads to the significant gap. And if it does not belong to L, then the final measured state giving 1 will be having some probability is less than equals to 1/3. Okay. So that means if final state is looks like that, say ket psi final is something like that, 0.71 plus 0.30. Okay, I'm writing 1 first, then 0. It's absolutely fine. If you want, you can write like 0.3 root over of 0.3 ket 0 plus 4 root over of 0.7 ket 1. That is absolutely okay. In that case, so the measurement or say projection, whatever you say, the projection operator for ket 0, it will be root over of 0.7. And that with, sorry, this was 1, sorry. With 0. And for psi final, it will be root over of 0.3. That means the probability of 1 will be root over of 0.7 square, which is this thing, 0.7 itself, or 70%. And similarly, this one will be, probability of 0 will be root over of 0.3 square. So it's 0.3 or it is 30%. Okay. So one prime example as I was talking. So it's kind of like say Shor's algorithm. Grover, I already said it to you. So Shor's algorithm, it actually factors a very large number. So it is used for factoring very large integer, which is a hard problem. Okay. So this in the classical base known factoring algorithm, it takes a super polynomial time. Or it's a variant of exponential. You can think it in this way. On the contrary, the quantum one that runs in polynomial time. And what was the definition of BQP? That is bounded error, quantum polynomial time, right? So Shor's algorithm belongs to the complexity class BQP. Sorry, it belongs to. Okay. Same thing applies for Grover's as well. Both follows the same type of model. Now the thing is, What about the problems where the answer is hard to find, but it is very easy to check? So the next one is, say the answer is hard to find, but checking the answer is easy. So this one is nothing but, of course, in context of quantum. Now, if you remember, these were the NP problems that we were discussing in classical. So in classical, this is the same thing which was your NP. So finding the solution was non-polynomial. It was difficult. But verifying whether it's a particular solution is correct or not, that was in polynomial type. So in classical, it is NP. But in quantum context, the same thing, where finding the solution through quantum is hard, but checking whether the one answer is correct in quantum context is easy. That is known as QMA class, which is quantum Marlin Arthur. Let me write it down in the next page. So that is QMA, or quantum Marlin Arthur. So it is a concept where we believe, say there is a Marlin. So Marlin is a powerful but untrusted prover. So Marlin is a powerful, but you cannot trust it. So it's an untrusted prover. What I am aiming for? I am aiming for checking whether an answer is easy or not. That was the concept. So say Marlin, he will be sending some quantum proof. Quantum proof is nothing but it's a quantum witness to Arthur. So Arthur will be taking that quantum proof, okay, and will run a BQP, or bounded error quantum polynomial verification circuit on the quantum proof. That is, it will check in the exactly same way, whatever we do. So P, BQP, some way they have a mapping. So similarly, NP and QMA, there is a mapping. So NP for checking a solution behaves in a P way. So QMA for checking a solution in a quantum context behaves in a BQP way. Kind of that. There is a mapping. So this quantum proof, on after verification, there can be two different kind of possible outcome. One is whether accept. If it is accept, then probability of accept will be significantly high, or it can be reject. But whether accept or reject, that will be in quantum polynomial time. Like the classical polynomial time, now it will be on the quantum polynomial time. That is, in a quantum Turing machine, it should be polynomial time solvable. Okay. So the definition of this QMA is something like, say, a language L will belong to the class QMA if there exists a quantum polynomial time verifier, which here is Arthur. There is a polynomial time quantum verifier, say V, such that if X belongs to L, there will be a quantum state which is nothing but quantum proof or quantum witness what is that? Get psi. Okay. Such that the probability that Marlin, on receiving the language X, And with the help of the quantum witness or quantum state psi, will accept it or will either reject it or say will accept it will be greater equals to 2/3. So the interpretation of this entire thing is the probability, this is the probability, this is the verifier, okay, this is a verifier. Sorry, this will be Arthur, not Martin. Arthur is a verifier. This is the language that I want to check whether it belongs to L or not. And this is the quantum witness. This entire thing is the proof. Now, if it is verified, then entirely, if this is true, then it will be accepted. Okay. And the alternate case, when X will does not belong to or X does not belong to L, in that particular case, if X does not belongs to L, for all quantum states, H psi is a general representation of any quantum state, then probability that the verifier with X and this quantum state psi will be equals to 1, and that will be less than equals to 1/3. So now there is almost the similar kind of thing like BQP, just a little more thing has been incorporated where finding the quantum solution with the quantum circuit may be difficult, or it is hard rather. But if I give a quantum like witness or a quantum a part of something to check or to verify, then it will be able to verify that one in quantum polynomial type. That is the thing. And BPP or bounded error probabilistic polynomial is a proper subset of bounded error quantum polynomial, and that is a proper subset of quantum Marlin-Arthur. Okay. Now there is only one left which I want to discuss. That is the quantum classical Marlin-Arthur. The next one. Okay. Let me check. Yes. So it's a QCMA. It is the quantum classical Marlin-Arthur. So now, so instead of sending the quantum witness or quantum proof, what if Marlin sends a classical string as witness or as classical witness? But Arthur will still be using some quantum computer to verify it. Okay. So now concept is almost like QMA, where a quantum witness was being sent to from Marlin to Arthur in order to verify that whether that particular quantum witness can be verified through the Arthur's verifier quantum circuit or not in polynomial time. That was a concept for QMA. But rather here it is, we are sending a classical witness from Marlin to Arthur, but Arthur will still be using some quantum computer to verify that whether that particular string can be accepted or not in order to verify that particular classical proof or classical witness. Okay. So the definition wise, it is like, what if, let me write, what if Marlin only sends a classical string, rather a quantum one. Now she's sending a classical string as witness to Arthur, but Arthur still uses some quantum computer to verify. Where it is very used? Where it is very used? It is used in these situations where the solution can be encoded, or maybe we have encoded the solution classically, but we are verifying them quantumly. So here, encoding of information is done classically, is in classical or done classically, but verifying the information is quantumly using a quantum computer. Okay, so if I have to illustrate it, say you want to verify a quantum circuit with high fidelity when run with a known input, and that input is a classical string. Okay, but to verify that output, you are using quantum resources. Or alternatively, you can consider it in this way. Say you are verifying some properties of a molecule, and the classical input is the configuration of atoms. That is, you have encoded the information classically. That is it. But you are computing the energy levels, or in order to compute the energy levels, you are actually relying on some quantum machine. Okay. So the definition is, if your X belongs to L, that is, it is a ES instance, then there will exist a classical string, a classical string. Purpose is not verified. Purpose for teleportation was to recreate the state itself. But yes, you can think something like that, that ultimately it's with some metric, with some quantum operator itself, it is ultimately verifying at Bob's level or receiver level that whether that was the intended quantum state that Alice wanted to send to Bob or not. Absolutely, you can think it in that way. So then there exists a classical string, say W, such that the probability that the verifier with X and the classical string, instead of this get side, right now it's a classical one. This is the classical string. Classical string will be equals to 1, and this will be having some probability greater or equals to 2/3. Okay. That means if X belongs to L, then there exists a classical string W, which is a correct proof that convinces. So in this case, the W convinces the verifier to accept the state with some high probability. High probability, which is a greater equals to 2/3. Okay. So here proofs are classical, but verification is in quantum. And success and failure depends on the bounded error. Because it is also like somehow we want to bound the error probability. We want to minimize it. Okay. That is the idea of QCMA. And I want to pause here. So this is kind of a brief introduction to quantum complexity classes. We have seen three major quantum complexity classes. A few others are there, which is a bit related to quantum cryptography, which is based on some zero knowledge, proof with respect to some quantum circuit. So once we will be doing that, if the scope permits, then I will be covering a bit of that class complexity classes. At least the theory wise, I will cover it. So next, and also the NP hard, and I hope all these like today's and yesterday's class, the concept you can now able to map, because a lot of terms are I'm using for like class to classes. So I hope it is now a bit at least clear to you. Go through these two videos multiple times in order to grab these concepts even more. And there is a lecture notes, you can follow it. It's of you can follow that one. Let me write it here itself. I'll not use another slide. Of John Watrous. Yes, John Electros. Okay. Well, not difficult, but yes, it's kind of new stuff, or it's an advanced version, advanced form of algorithm, advanced versions of Turing machine, advanced versions of complexity classes. So it's an advanced versions of the classical as well as a part of the quantum ones. Absolutely. Okay. So, and it is of the lecture notes of this one on the quantum complexity theory. Okay. There are YouTube lecture links of professor as well. So it's of quantum complexity theory. Okay. He's from University of Waterloo. You can definitely follow his lecture. Okay. So I'm to pause here. Yes, things are little difficult and different, of course. Thank you so much, everyone. So we will again meet, I guess, on coming Monday.
Hello, am I audible, ma'am?
Yes, sir, you're audible.
Yeah, yeah. So I think it's end of the session here. So thank you so much, ma'am, for this session. And the next session will be on Monday, again taken by you. So thank you so much. I think most of the questions and queries are already handled. So thank you so much, participant. That's all for this session, and you all